Hey there, analytical chemists. I'm Dr. Swarthout, and I'm going to be running through our pre-lab lecture material for our final experiment for the semester, the analysis of phthalate esters. And I'm going to switch over and share my screen here. And walk through this lecture material here. So our final experiment, we're going to be analyzing phthalate esters using gas chromatography with flame ionization detection, just like we did in that first experiment of the semester where we were analyzing ethanol content in wine. It's going to be a little more complex this time because instead of having one analyte, we're going to have 4 analytes for each group. And phthalate esters are these compounds here. I've got a couple of examples, but they have this general structure of this phthalic acid group substituted with 2 organic moieties here, R and R prime. And these can span a great range of different types of organic groups. So, this example over here has 2 phenyl groups. This one here has 2 alkyl chains. And then we have also some branched versions over here. So they can be a wide variety of different structures that impart different properties onto the plastics that they're used in. And the image that I have in the background here is one of some microplastic fragments floating around in a water sample. And one of the reasons you'll see that we're concerned about these, I'll get into in a moment, is that these phthalate compounds can leach from the plastics that they're used in into the environment and cause some risk for organisms that are exposed to these. All right, so what are phthalates used for? These are commonly used in polyvinyl chloride compounds or plastics or silicone plastics, and they're used to make the plastics to alter the physical properties of those plastics. So this could be to make them more malleable, more flexible. It could be to make them more durable. It could be to change their color or their transparency. They're used for a lot of different reasons. But we are concerned about these because they are so commonly used, and they're in products like things like water bottles, or baby toys, or personal care product packaging. We're concerned that they might be getting into, or we might be exposed to them as humans. There's some evidence showing that they cause some health impacts in humans or other animal systems. So the big concerns here is that they mimic estrogen. So if we look at the structure of estrogen here and kind of compare that to some of these other phthalate compounds, we can see that it does have this kind of like single aromatic ring group with some other ring-like structures in these phthalates that allow them to perform the similar functions to estrogen in the body. And when they're metabolized, the structures of the metabolites start to resemble estrogen even more closely. So what most studies have shown is that these phthalates can disrupt endocrine function in humans and other animal systems. So this leads to things like changes in some of the organs in our bodies that are involved in endocrine regulation, as well as a lot of reproductive impacts. So one of the big things that caught the attention of the world a while back with phthalates was fish that are exposed to high levels of phthalates. Male fish can start to exhibit traits that are exclusively female. So turning little boy fish into little girl fish. And we're concerned that similar impacts might be taking place at a smaller scale in human systems. All right, so with that said, what we're trying to do in this experiment is give you a chance to get some hands-on time with instrument method development. So you're going to develop a GCFID method to separate out 4 different phthalate compounds that we are going to give to you guys. And then a secondary goal of the experiment is to compare 2 different quantitation methods. So for the majority of the semester, we've just been doing external calibration. But we're going to introduce standard addition calibration in this experiment, and you guys are going to compare the results of those 2 calibration methods. All right, so I want you to remember some details about GCFID from our first experiment. And I am going to switch over and play this video that takes about 3 minutes here to give you a refresher on what GCFID is, how it works.
Gas chromatography, GC, is a common type of chromatography used in analytical chemistry for separating and analyzing compounds that can be vaporized without decomposition. In gas chromatography, there is a mobile phase which is a carrier gas, such as helium, nitrogen and argon. And there is stationary phase, called a column, which located in an oven where the temperature of the gas can be controlled. There is also a detector that measures analytes in a gas stream attached to the GC system. The flame ionization detector is almost universally employed, where the flame commonly is generated with hydrogen and air. The auto-sampler provides the means to introduce a sample automatically into the inlets. Also, manual insertion of the sample is possible. The column inlet, or injector, is attached to the column head and provides the means to introduce a sample into a continuous flow of carrier gas. In the injector, a sample is introduced into a heated chamber via a syringe through a septum. The heat facilitates volatilization of the sample and sample matrix. The carrier gas then either sweeps the entirety, splitless mode, or a portion, split mode, of the sample into the column. In split mode, a part of the sample carrier gas mixture in the injection chamber is exhausted through the split vent. In splitless mode, all the sample carrier gas mixture in the injection chamber is transported through the column. Two types of columns used in GC: packed column, where the stationary phase is coated directly in the column, and capillary column, where the stationary phase is coated with the inner wall of the column. The mixture separation is based on differential partitioning of the components between the mobile and stationary phases. The component which has less affinity to the stationary phase, consequently less interaction, travels faster and eluted out first. And the component which has more affinity to the stationary phase, consequently more interaction, travels slower and eluted later. In addition, other factors influence the separation of the components, such as column temperature, carrier gas flow rate, column length, and amount of material injected. As compounds elute from the column, they interact with the detector. Different types of detectors can be used, such as the flame ionization detector, thermal conductivity detector, and mass spectrometer detector. The operation of the flame ionization detector is based on the detection of ions formed during combustion of organic compounds in a flame, which generated by hydrogen and air. To detect these ions, 2 electrodes are used to provide a potential difference. The positive electrode doubles as the nozzle head where the flame is produced. The other, negative electrode, is positioned above the flame. When an organic compound is mixed within the hydrogen flame, mainly carbon ions are generated. And a current is produced between the electrodes proportionally to the amount of organic compound present. This current is measured with an electrometer, amplified into proper voltage, and fed into an integrator. The manner in which the final data is displayed is based on the computer and software. The number of peaks present can indicate how many components are in the mixture. Usually, the x-axis of the gas chromatogram shows the amount of time taken for the analytes to pass through the column and reach the FID detector. Typically, the y-axis, or the area of the peak, is a reflection of the amount of a specific analyte that's present.
All right, so please forgive the kind of automated voice there and the horrible pronunciations of words like chromatogram is not a chromatogram. But the animation there is probably the best that I've seen. So hopefully it gives you some refresher on how GCFID works. So let us get back here. All right, so one of the things that they don't really discuss in that video, but that's important for our experiment, is that the separation of those compounds is facilitated by the temperature of the GC oven. And there are two general ways in which you can run a GC. You could use an isothermal temperature program, which maintains a single temperature for the entirety of the GC run. Or you could have a ramped temperature program. In this case, you're going to change the temperature over time, and you can have multiple ramps and hold times in here. So this has a single ramp up to a high temperature, and then it holds for a certain amount of time. And then the run ends and the temperature comes back down to its starting. So some of the issues you might see with isothermal conditions are things like in this top image here. If you let the sample run for a long time, you might end up with some really bad peak broadening towards the end of the sample run. If you run it for a short time, sometimes you get very poor separation between your analytes, and you get peaks that are kind of running into one another here. Oftentimes, both of these problems can be solved by using a temperature ramp program. So down in this bottom panel, you can see all of these peaks have now been separated because we've kind of achieved a balance between the total runtime and the separation of the peaks based on starting at a low temperature and ramping up to a high temperature.